Hello everyone and welcome. In this video we are learning about Maserati's fascinating new engine, a twin-turbo V6 that uses dual combustion chambers, with a pre-chamber igniting the main chamber for more efficient, more powerful combustion. This engine is going in the Maserati MC20, a car that was developed in the heavens using emergency blanket technology, brought down to earth, sculpted in expensive Italian Play-Doh, gift-wrapped with the same attention to detail you're used to on your own presents, and now displayed proudly to eyes around the globe through the internet's best free video site. Now, pre-chamber combustion is nothing new. Honda was using a similar technique in the 1970s, but Maserati has a unique approach to using pre-chambers in gasoline engines so that they can meet today's emissions requirements while still providing horsepower benefits. So I don't know of any current production cars out there using pre-chamber combustion technology. However, there are engines out there which are using active pre-chambers versus what Maserati is doing using a passive pre-chamber. And so the main difference there being the active chamber can either put in fuel or air or both into the pre-chamber, and Maserati's system just has a spark plug with that pre-chamber. So it's not actively putting fuel or air into that chamber. So how do these active systems work? Well, the process is as follows. So you have two fuel injectors, one for the pre-chamber and one in your intake port. And what this initial fuel injector is doing is getting in a very lean air-fuel mixture. So super lean, otherwise it wouldn't be combustible in a typical combustion engine. So a very lean air-fuel mixture that's coming in during that intake stroke. And then you're going to pull in that air and fuel, compress that air and fuel with the piston, and then you have a separate injector which is going to spray fuel directly into this pre-ignition chamber. So now what you've done is you've created a rich air-fuel pocket in this pre-chamber, and then you have a very lean air-fuel ratio in the main chamber. And so you use the spark plug to ignite that air-fuel mixture, and what it does is it creates these turbulent jets. The pre-chamber has these little ports at the bottom of it, so that combustion comes spewing out in these turbulent jets, and because it expands over this wide area of the main chamber, it's able to actually burn off that lean air-fuel mixture. Whereas traditionally, if you just had a spark plug in there, you wouldn't have consistent combustion. That combustion would spread very slowly. But because you shoot out these flames into the whole chamber, you're able to actually burn it. And so the advantage of this is that you're able to use lean air-fuel mixtures that you otherwise wouldn't be capable of burning, meaning you're using less fuel overall, and thus it's a very efficient design. Now, the challenge here is that for catalytic converters, which of course you need on an emissions compliant road car, they don't like lean air-fuel mixtures. They like it when the air-fuel mixture is right at stoichiometric ratio 14.7 to 1. That is where catalytic converters operate in their most efficient region. And so because of that, using something like this is very difficult to do in a road car from an emissions standpoint. Now, before we move on to how the passive system works in the Maserati engine, first let's just cover the general specs of the engine. It's a 3.0 liter twin-turbo 90-degree V6 engine. It's making 620 horsepower and 730 newton meters of torque with an 11:1 compression ratio and using relatively wide cylinders, each with an 88mm bore and an 82mm stroke. The engine revs up to 8,000 RPM, making over 200 horsepower per liter. So how does a passive pre-chamber work? Now again, passive simply means there isn't air or fuel directly injected into that pre-chamber. And so how does it work with the Maserati? Well, basically you're going to have an option of either port injection, direct injection, or both. In this case, Maserati is doing both. And you then have an air-fuel mixture coming in, whether it's from the port or the combination with the direct, of 14.7 to 1. So you're at that ideal stoichiometric air-fuel ratio, which is the whole key to this thing, is that it's able to pass emissions because it's operating at that ratio. And so how does that air-fuel mixture get inside of this pre-chamber? Well, that happens during the compression stroke. So you have this piston come down, pull in that air and fuel, and then press that air and fuel together into that pre-chamber as well as the main chamber. And so then you have your spark ignite, that normal ideal air-fuel ratio, no problem for the spark, that comes down and then shooting out those turbulent flames, which then causes you to have very quick combustion of the rest of the air-fuel mixture. So the whole idea of this strategy is to speed up combustion, and by doing so, by reducing the time it takes for combustion to occur, you're reducing the likelihood of knock to occur. And so Maserati says, according to their patent on this engine, that by using this strategy, they're able to increase their compression ratio by 15%. And the big kicker of all of this is that unlike this active system, it's able to meet emissions. Now, also according to their patent, they're able to reduce fuel consumption by 30% or have an engine downsized by about 25%. So you can make the same horsepower in a 1.5 liter inline 3-cylinder that you could with a 2.0 liter inline 4-cylinder. So you'll notice that there are two spark plugs, one on the side of the cylinder and one on top of the cylinder in the pre-chamber. And actually, if you were to look at the layout from above, they wouldn't be on opposite sides here. The spark plug is going to be over here between those two valves, and then you'll have your direct injection on the side as well as your port injection with the intake. But just simplified drawing here so you can see it all in one image. But you have these two spark plugs, and we'll get into the strategy that they use a little bit later on in this video. But the reason why this is done is to stabilize combustion at low loads. So at low loads, they actually use both spark plugs to make sure they have complete combustion, and then with higher loads, they're just using this top pre-chamber. And because they're using that ideal air-fuel ratio, you don't have to use an injector in the pre-chamber because you don't have to build a little rich pocket. You already have an ideal air-fuel ratio in that pocket for the spark to ignite. Now you'll also notice that it has dual fuel injectors. So why is it doing this? Well, by using a port injector, that gives it plenty of time to mix the air-fuel ratio. And by doing this, it eliminates the need of having tumble ports where the intake air is caused to tumble as it enters within the cylinder. When you use direct injection, you have less time for that air and fuel to mix, and so you use tumble ports in order to have that air swirl so that you can mix that direct injection fuel. The challenge with this is those tumble ports can restrict your airflow coming in, which isn't ideal for engines that are going for high horsepower. And so in this scenario, they use the port injector to help mix that air-fuel mixture, but you're using the direct injection in order to get that charge cooling effect. So as that fuel is sprayed in and vaporizes, it cools the air in the combustion chamber, which helps it produce more power by reducing the likelihood of knock. And so that's why they're using this strategy. The strategy allows them to use, more traditional ports here for the intake air so they can have plenty of air coming through. Now, a few additional facts about this pre-chamber. According to the patent, they're using a volume of about 0.3% to 0.5% of the cylinder for the pre-chamber. So if you had a 500cc cylinder like this engine is using, well, the pre-chamber is about 1.5 cc. And so the reason why it's using a very small pre-chamber versus the larger one that you'll see in these active systems is that limits the overall surface area. And by limiting that surface area, that means you're not having as much heat wasted and lost. And you do actually have coolant jackets around that pre-chamber to help make sure it doesn't get too hot. And one other aspect of this pre-chamber, because it's small, actually there's a bit of a sweet spot in how quickly you want combustion to occur. So the larger this pre-chamber, the more forceful your jets are going to be coming out of it, and so they kind of want this smaller size to not have that excessively fast combustion. We'll get into the logic of why you want to be able to kind of control that a bit later, but looking at the pre-chamber, there's about 6 to 9 holes according to the patent. They're about 0.8 to 1.8 millimeters in diameter, and coming off the axis of the pre-chamber, they're at about 0 to 80 degree angles, and they are sized for the top end. And then of course you have that second spark plug, which is required for that bottom end, those low load scenarios. Okay, so getting into the logic of when they're using both spark plugs and when they're just using one spark plug. So here we have a plot, we're looking at RPM on the bottom versus load or your torque percentage here on the vertical axis. And so there's two different scenarios here. When you're at high loads at pretty much any RPM above about 20 to 40% load, whatever RPM you're at, if you're above that, then you're going to be using just the pre-chamber spark plug for maximum power. And then below that, in order to have low load stabilization of that combustion, you're going to be using both spark plugs. So you'll actually fire the main chamber spark plug first, and then the pre-chamber spark plug a little bit later. Now, one of the interesting things you can do by changing the delay between when you fire this spark plug and when you fire this spark plug is you can change the duration of combustion. So the earlier you fire the main chamber spark plug and the longer delay you then have until you fire the pre-chamber spark plug, the longer combustion is going to be. And so you're going to have a slower combustion versus if you fire them both fairly close together, you're going to have more rapid combustion occur. And so you can use this to your advantage. If you're trying to go for a bit more power, a bit more efficiency, then you of course want to speed up that combustion. But when you just start a cold engine, you want to get that catalytic converter up to temperature really quickly. And so what you do is you slow that combustion down by delaying between when you fire each of the spark plugs, and this gives you a long combustion, and that gives you higher exhaust temperatures, which heats up your catalytic converter, making it effective much more quickly. So to summarize the advantages of this style of engine, the big one they're going for, reduced likelihood of knock, thus allowing you to make more power, have faster combustion, and operate more efficiently. You're able to control the duration of combustion, which not only is helping you control when that catalytic converter is up to temperature, but it also allows you to reduce noise. So when you're at low load, you can slow down combustion and have the engine be a bit more quiet, somewhat important for luxury vehicles out there. Now, as far as the bad stuff, of course, there is a complexity to this. You know, you've got dual injectors for every cylinder, you've got dual spark plugs for every cylinder, you have this pre-chamber, so the complexity is there. The other thing that I'm kind of curious about and how effective it will be long term is this pre-chamber, right? Because there's nothing really causing it, forcing it to clear out except for just pressure differences. So when you're pressing that air and then combustion is occurring, I'm wondering, you know, how much is getting left behind in this pre-chamber and not just kind of refreshed every single cycle. So I am curious about that and long term what happens. But of course there's testing that goes into these before they just get released out. So we will see, time will tell how these engines do. But it is a very fascinating technology, and it's really cool to see this kind of innovation in a road car. So thank you all so much for watching, and if you have any questions or comments, of course feel free to leave them below. And to the EV folks out there wondering why are they doing all this, guess what? There's going to be an EV MC20.